Okay, let us continue the second part of today's course or class. Okay, in the first part of today's class, we have taught to here, okay, where h of d is the differential entropy of a Gaussian random variable with variance d. This lower bound, okay, here is the lower bound. Okay, r of d is greater than or equal to h of x minus h of d. Is extensible to sources with memory and other distortion measures. One important feature of the SLB, okay, that is Shannon lower bound SLB, is that it is asymptotically tight in the low distortion. Okay, excuse me. In the low distortion region for a wide class of sources, and in some occasions it actually coincides. Okay, what is the meaning of this word coincides? Okay, let us see the following problem. Okay, problem 12. What is coincides? Solution: to be the same or similar. Okay, let us go back to the word coincides. Okay, with the rate distortion function. Okay, so what does it mean? Okay, it means, okay, let us go back to the last page, page 19. Okay, it means the Shannon lower bound. Okay. Okay, Shannon lower bound. Shannon lower bounds can generally be found if the distortion between any two numbers can be expressed as a function of the difference between the value of these two numbers. Okay. The Blehart-Arimoto algorithm. Okay, what is this algorithm? Let us see. Oh, sorry. Okay, Blehart. Okay, let us see problem 13. What is Blehart-Arimoto algorithm? Okay, solution. Oh, I have some display problem. Okay, so let me search. Okay, for the Blehart. Okay. Okay, the display is restored. Okay, problem 13. What is Blehart-Arimoto algorithm? Solution: the term Blehart-Arimoto algorithm is often used to refer to a class of algorithms for computing numerically either the information theoretic capacity of a channel, the rate distortion function of a source or a source encoding, that is, compression to remove the redundancy. They are iterative algorithms that eventually, okay, that is, finally, converge to one of the maxima of the optimization problem that is associated with these information theoretic concepts. Okay. History and application. For the case of channel capacity, the algorithm was independently invented by Suguru Arimoto and Richard Blehart. In addition, Blehart's treatment gives algorithm for computing rate distortion and generalized capacity with input constraints. That is, the capacity cost function analogs to rate distortion. Okay, we know that the rate distortion function is a relationship between the rate and the distortion. So similarly, the capacity cost function is a relationship between the capacity and the cost. These algorithms are most applicable to the case of arbitrary finite alphabet sources. Okay, for example, if the source is 0 and 1, okay, the bits, okay, then the alphabet is 0 and 1. So there are only 2 alphabets. Okay, so it is an example of finite alphabet sources. Much work has been done to extend it to more general problem instances. Okay. Recently, a version of the algorithm that accounts for continuous and multivariate outputs was proposed with applications in cellular signaling. There exists also a version of Blehart-Arimoto algorithm for directed information. Okay. Algorithm for rate distortion. Okay, suppose we have a source x with probability p of x of any given symbol. Okay, p of x is the probability mass function of x. Okay, you can see x as a random variable. We wish to find an encoding p of x hat given x. Okay, that is, the original symbol is x, and after the encoding, the output is x hat. That generates a compressed signal x hat from the original signal, while minimizing the expected distortion, that is d of x hat, where the expectation is taken over the joint probability of x and x hat. Okay, we can find an encoding that minimizes the rate distortion functional locally by repeating the following iteration until convergence. Okay, what is functional? Okay, the functional means the function of a function. For example, the Fourier transform is a kind of functional. Okay, because the Fourier transform maps a time domain function into its frequency domain representation. So Fourier transform is a kind of function of function. Okay. Okay, next, p or pt plus 1 of x hat is equal to summation, okay, over all possible x. P of x times pt of x hat given x. Okay. and pt plus 1 x hat given x is equal to pt of x hat. Okay, so the t means the tth iteration, and the t plus 1 means the t plus 1 iteration, times exponential minus beta times d of x hat over summation x hat, that is over all possible x hat, pt of x hat times exponential of minus beta times d of x hat, where beta is a parameter related to the slope in the rate distortion curve that we are targeting, and thus is related to how much we favor compression versus distortion. Higher beta means less compression. Okay, so this is the Blehart-Arimoto algorithm. Okay, let us go back to the first time where the Blehart-Arimoto algorithm appears. Okay, the Blehart-Arimoto algorithm, co-invented by Richard Blehart, is an elegant iterative technique for numerically obtaining rate distortion functions of arbitrary finite input output alphabet sources, and much work has been done to extend it to more general problem instances. Okay. When working with stationary sources with memory. Okay, what is a stationary sources? Okay, that means the distribution of the source does not change with time. Okay, this is called the stationary sources. And what is a source with memory? Okay, we have introduced a memoryless source. That is, the value of the source at time t is independent of the value of source at time t minus 1 and t minus 2 and etc. So a source with memory means that the value of the source at time t, okay, is related to the value of the source at time t minus 1 and t minus 2 and etc. It is necessary to modify the definition of the rate distortion function, and it must be understood in the sense of a limit taken over sequences of increasing lengths. Okay, R of d is equal to limit n approaches infinity, Rn of d. Okay, where Rn of d is equal to 1 over n and infima of Qyn given Xn, which is in the set Q, and the I of Yn Xn. Okay, we have learned I, it is the mutual information, and the set Q is equal to Qyn given Xn of Yn given Xn x0, such that the expectation of d of xn yn is smaller than or equal to d. Okay, and d is the distortion. Okay, we will explain later, explain what is d of xn yn in the problem. Okay, let us see this problem. Problem 14. What is d of x n y n? Okay. Solution: d of x n y n is a distortion function. Distortion functions measure the cost of representing a symbol x by an approximated symbol x hat. Typical distortion functions are the Hamming distortion and the squared arrow distortion. Okay, first let us see Hamming distortion. The Hamming distortion is defined as this equation: d of x hat is equal to 0. If x is equal to x hat, and d of x hat is equal to 1 if x is not equal to x hat. Okay, next let us see the squared arrow distortion, which is defined as this equation: d of x hat is equal to x minus x hat and square. Okay. Let us go back to the d. Okay. Function. Okay, d function. So this means the expectation of the distortion function is smaller than or equal to a given distortion, capital D, where superscripts denote a complete sequence up to that time. Okay, we can see that here is the superscripts yn and xn. That is the complete sequence up to time n. Okay, so this is the same for yn, xn. Okay, and yn, xn. Okay, and here is the yn and xn, and here is the yn, xn and yn, and the subscript 0 indicates initial state. Okay, so this is x0. It is the initial state. Okay, finally we have introduced what is the rate distortion function. Okay, it's a long solution. Okay, let us go back to the slides. Okay, so we have spent many time to explain what is a Gaussian source and what is the meaning of this sentence. Okay, if you have any questions, please do not hesitate to contact me. Then, when adopting the mean squared arrow as the distortion metric, we can measure DIS as. Okay, what is DIS? Okay, let us go back. Okay, DIS is the source. Okay, DIS is the source encoding distortion. Okay, the S means source. Okay, we can measure DIS as, okay, DIS of XIS. What is XIS? Let us review it. Okay, XIS is the source encoding rate. Okay, it is equal to eta times 2 to the power of minus 2xi. Okay, where xi is the xis, okay, is the same. Where eta is the maximum distortion, okay, equal to the variance of the synthetic Gaussian source. Okay. On the other hand, the channel-induced distortion DIC is due to errors introduced during transmission over the wireless channel that cannot be corrected by the error correction mechanism. Okay, we can know that each error correcting code has its limitation. That is, for any error correction code, it cannot correct infinitely many errors. Okay, it can only correct finite errors. Okay, it is a nature of the error correcting code. So there must exist some errors that cannot corrected by the error correction mechanism. Excuse me. Okay, when assuming that these errors are concealed by replacing the Earth source samples with their expected value, the channel-induced distortion is a constant equal to the variance of the source samples. Okay. The impact of DIC. Okay, what is DIC? Okay, let us review it. Okay, DIC is the channel-induced distortion. That is, the distortion caused by the channel. Okay, the impact of DIC on the end-to-end distortion is determined by the probability that an uncorrectable transmission error occurs, which we denote by PRIE. Okay, here PR means the probability, and E means the error. And I, what does I mean? Okay, let us review. Okay, the I is the index of the secondary user, where 1 is smaller than or equal to I, and I is smaller than or equal to capital N. And what is capital N? Okay, the capital N is the number of secondary users. Okay, let us go back to this slide. Okay, PRIE. Furthermore, PRIE depends on both the channel SINR gamma IS. Okay, what is gamma IS? Let us review it. Okay, gamma IS is the SINR for secondary user I, and the channel coding rate RIS, okay, which determines the strength of the channel coding. Okay, we have introduced what is the channel coding rate. If you forget it, please review the handout. Also, it is worth noting that given a channel throughput, capital RIS, and a fixed channel coding rate, small ris, the best effort source encoding rate can be determined as XIS is equal to RIS, small ris times capital RIS. Okay, so we can know that for the channel throughput, okay, capital RIS, okay, when it multiplied by the channel coding rate RIS. Okay, for example, if the channel coding rate is equal to 1 second, that means for one input bits after the channel encoding, we have 2 output bits. Okay, so for the channel throughput capital RIS, the real information bit rate is capital RIS times 1 second, and this is equal to the source encoding rate. So now we know that, okay, it is 25 minutes. Let us take a break.